The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let me first remind you what we did at the end of last lecture. Say, suppose you consider a stream moving in some space-time M, say with the following metric given by G mu, and the coordinate which I denoted by x nu. So nu typically will go from, say, mu nu go from 0, 1 to d minus 1, and capital D will be the number of space-time dimension. And then the worksheet will be characterized by this x mu as a function of worksheet coordinate sigma tau. Then this describes a mapping of a two-dimensional surface embedded in the full space-time, in the full space-time. And I will also use the notation that x mu equal to sigma a, and sigma a will be sigma 0, sigma 1, and equal to tau and sigma. Okay? And then the simplest action, which have a clear geometric meaning, is essentially just the action is given by the area of the surface. It's given by the area of the surface. And this delta H is the induced metric. So if you have an embedding in this space-time, then this embedding will induce a non-trivial metric on the worksheet. So this H is the induced metric on the worksheet. And then if you take the determinant of it, then essentially give you the area element on the worksheet. But we also show that classically, this action is equivalent to this action. You can rewrite it by introduce something like a Lagrange multiplier, like gamma AB, and then by eliminate gamma AB, then you cover this. Okay, and the equation of motion for the gamma AB. Yeah, if you solve the equation for gamma AB, essentially you get something like this, lambda HAB. And lambda is arbitrary constant, arbitrary function. Right. Okay. Yeah, say if you solve the equation of motion for gamma AB, and then that's what you get. So this final form, so this is the action we will use to quantize it, is because this action have a nice polynomial form, not like this action, which is a square root is always awkward. And so this have a nice polynomial form. And when you quantize the action, say if you do path integral quantization, then you need to integrate both dynamic variables, say exponential is, p, gamma, and x. Okay, so both are dynamic variables. When you quantize, you have to path integral over all of them. And so let me just say a little bit more about the geometric, which we mentioned at the end last lecture, the geometric meaning of this action. So if you just look at this action itself, this is just like a scalar field in a two-dimensional curved space-time. And this two-dimensional curved space-time have a non-trivial metric which is given by gamma. And the scalar field is just this x. Okay? So this gamma can be considered as some kind of intrinsic, can be considered as an intrinsic worksheet, intrinsic metric on the worksheet. And then this x then describes the embedding of this, describe this embedding of this worksheet in space-time. But x, from the point of view of this two-dimensional worksheet, it just behaves like a scalar field. It just behaves like a scalar field. So when we quantize this action, so when we do the path integral, if you just pass into if you just do the path integral over dx, then this is just like a standard two-dimensional quantum field theory. Okay, just like a standard two-dimensional quantum field theory. But what's unusual here, when you quantize a string, because the gamma is also dynamic variable, you also have to integrate over gamma. And this makes it more non-trivial. And then this is no longer like a just like quantizing the scalar fields. And because you are integrating over all possible intrinsic metric on the worldsheet. So this is like quantizing so this is like quantizing 2D gravity. When you integrate over all possible metric, then this is like quantizing gravity. But this is only the gravity on the worldsheet. Coupled to D scalar fields. Okay? Yes?
So in what sense is it 2D gravity? Because the metric is like a D by D object.
No. The metric, no, this is a two-dimensional. Gamma is a two-dimensional metric. It's an intrinsic metric on the worldsheet.
Yes.
Yeah, so this 2 by 2.
I see.
AB is only goes 2 by 2. AB is only going from 0 to 1.
Oh, yes.
Yeah, so AB only runs over the worldsheet 0 to 1. 0, 1. Yeah. So once you write that form, then you introduce an intrinsic metric on the worldsheet. Then you introduce an intrinsic curved space-time on the worldsheet. And when you integrate over all possible metric, then that's corresponding to take into account the fluctuations in the metric.
Yes.
From this two-dimensional point of view. So that's why we say this is like quantizing 2D gravity. Okay. By gravity, we just means the space-time. Okay, is this clear? So now we see the question of quantizing the string theory essentially boils down to quantize this two-dimensional gravity on worldsheets coupled to these d-scalar fields. And this d-scalar field describes the embedding of your worldsheet. Okay? So we will consider a simple example. We will consider example which M is just Minkowski space-time, d-dimensional Minkowski space-time. Okay? So in this case, G mu mu becomes simple, just equal G mu mu, eta mu mu. And then this Polyakov action can also be simplified. So this SP now just become 1 over 4 alpha prime T square sigma gamma AB partial A x mu partial B x mu. So now when I write this x mu should be understood that they are contracted by the standard Minkowski metric. Okay? So now this really, if you just look at the x, this is like a free scalar field theory because the dependence on x is purely quadratic. So this is like a free scalar field in curved space-time. Okay? In curved worldsheet. 2D worldsheet. Okay, in 2D worldsheet. Okay. So there's still slightly unusual thing about this scalar field theory from our standard one. Yeah, actually, I might be missing minus sign somewhere. I might be missing overall minus sign. I think I'm missing overall minus sign. Just let me put it here. I think I'm missing overall minus sign. That for our current purpose, it does not matter. But I think for the later purpose, we need it. Okay? Because if you consider standard field theory using this -1 matrix, then I need the minus sign. Okay? So this is just like a free scalar field theory with, in this 2D curve space-time. But there's slightly thing unusual about this one. So there are two unusual things. One is that we also need to integrate gamma. But there's another usual thing, even from the perspective of scalar field theory, is that if you look at the zeroth component of x, because eta 0, 0, so we are using the eta equal to minus 1, 1. Okay? Because eta 0, 0 is a minus 1, so the zeroth component of x will have an opposite kinetic term to the other component. Okay? So you might have learned in your quantum field theory class that actually you cannot change the sign of your kinetic term, otherwise you get instability, because then your Hamiltonian will be unbounded from below, etc. So this action, so our story here have two unusual features. One, you have to integrate over gamma, and the second is that one of the scalar fields have the wrong kinetic term. Okay, the sign of the kinetic term is wrong. We will see that these two features actually solve for each other, and this is actually a consistent theory. So this is actually a consistent theory. Any questions at this point? Okay, so before you do any theory, what you should do, so before you say work on any theory, what should you do first? No, that's too far away. Just the first thing you should do. After you write down the action of Lagrange, what should you do?
So the equation of motion.
That's still too far away.
Check units.
That's something what you should do. Yeah, but that you do in kindergarten. So it's not included here.
Constants of motion?
That's close. What is responsible for constant of motion?
Symmetries.
Yeah, that's why symmetries. You first have to analyze the symmetries. Okay, so that's what we will do. Okay, let me call this equation 3. Just continue from my my notation of last week. Yeah. So first we should analyze the symmetry of this action. So first, so this is a mapping to a Minkowski spacetime. The Minkowski spacetime itself have a Poincare symmetry, and that Poincare symmetry will be reflected here. First, we have a Poincare symmetry. Of x mu. In other words, this action is invariant. If you take x mu to go to x mu plus a constant, okay? Say a mu is a constant. So it's obvious this is invariant, okay? Because everything acting on mu x with a derivative. So if you shift by x mu with a constant, then of course that's a symmetry. And also this is invariant under Lorentz symmetry. Okay, so lambda is the constant Lorentz symmetry, Lorentz transformation. Okay, so this is also self-evident because if you have because of this contraction, if you make a constant Lorentz transformation, you don't see the derivatives, and this is contracted as a Lorentz scalar, then this is invariant. Okay. So this is the first set of symmetry. The second set of symmetry, essentially by construction, because we are writing this as a scalar field in the curved space-time, then this is invariant. Then this have invariant and a two-dimensional coordinate transformation. And in other words, this is invariant under reparametrization of the worldsheet. Okay? So this is essentially a necessary condition which should satisfy by any string action, because as we said before, sigma tau is just parameterize your worldsheet, and your action should not depend on how you parameterize it, and that parameterization should be arbitrary. Okay, should be arbitrary. You should be able to change your parameterization. Yeah, because if you think about the surface in space-time, no matter you can say parameterization corresponding you put the grid on this surface. Whether you do this way or you do it some other way, it should not change the surface, the property of surface itself. So that means the action itself should be invariant under reparametrization of your worldsheet. And the parameterization of the worldsheet translates into just arbitrary coordinate transformations. So sigma and tau should be able to say, if you make arbitrary coordinate transformation, and the action should be invariant. Okay? And this is by construction. And this is action by construction invariant. And this nambu-goto action. And this Polyakov action we obtained by rewriting this nambu-goto action is also by construction because it's manifest, because this is like a covariant curve space action for scalar fields. So this is automatically invariant under the coordinate transformation. Okay? And under this coordinate transformation, this x mu just transforms as a scalar field. So the scalar field transforms, say, as the following. It's going to x mu prime. And x mu prime, when you evaluate it at the new coordinate tau prime and sigma prime should be the same as your original x evaluated at the original location. So this is essentially the definition of a scalar field. He said that when you make a coordinate transformation, if you follow the point, the value of x does not change. Okay, because when you go to the new location, the x prime evaluated at new location should be the same as your original value. Okay? Yes?
So basically we have diffeomorphism invariance in the real space and the worldsheet. That's like A's.
No. This is not diffeomorphism invariant in the world. No, this is not diffeomorphism invariant. This is
special case of diffeomorphism.
No, this is not diffeomorphism. No, this is not diffeomorphism. This is global symmetry.
Oh yeah, okay. And also, do we ever consider curved real space?
Yeah, you can consider a curved space. But right now we are at the high school level of string theory class, and if you go to curved space, that should be college level of string theory. It's beyond what we are doing right now.
But in the curved space, we don't have Poincare symmetry. Well, we have Poincare.
Yeah, then you don't have Poincare symmetry.
Yeah.
So this is specific to this action. Yeah. But this is general. Yeah. So, of course, under this coordinate transformation, this gamma AB should transform as a tensor, as in standard in GR. This evaluated gamma prime evaluated new point should be related as a tensor. Okay, so you can check yourself. This is essentially by construction, but you can check yourself that the action is indeed invariant under those transformations. Okay.
Is there also gauge symmetry to this? How we add a phase to x and the derivative with a cancels?
Sorry.
Is there any gauge theory in?
Gauging what? Gauging which one?
X. Like equation 3, cause like we add a global phase to x and the derivative with a and
No, x is real here. This is our full action.
x is okay.
Yeah, this is our full action and x are real. Yeah. So this is invariant on that. I will not show this is invariant. This is just essentially by construction. You should check it yourself if you are not convinced. So the third symmetry is called the Weyl scaling of gamma AB. So the third symmetry is slightly surprising. So under this symmetry, x mu does not change, but the metric, we multiply it by overall prefactor. And this omega is for any function. Okay? So this is a very important symmetry, so let's check that. So when you multiply the gamma by overall prefactor, when you go to gamma AB, then that's giving you the same prefactor but with a minus sign here, okay? And now in the determinant of gamma, then that gives you the square of this, and then take the square roots, then give you a positive power, then they cancel. Is it clear? So the negative power here cancel with the positive power here, okay? So this thing is invariant. So this thing is invariant on this scaling symmetry. So the way to see that, another way to understand that somehow this action, so the same thing with this action, this is not specific to we are working with Minkowski space-time. The same feature here only depends on these two, okay? So the same thing happens here. So you can also see a feature why. You can also get a feeling why this is such a symmetry just by looking at the relation between the nambu-goto action with this action. So in this nambu-goto action, there's no gamma, okay? So in some sense, you can say this is automatically invariant under this kind of symmetry because there's no gamma. And now we see that the equivalence, when you write down equation motion, to go from here to the nambu-goto action, the equivalence between them, they can be related by arbitrary function lambda, and related by arbitrary function lambda. This is another way to see this symmetry. Okay, it's another way to see this symmetry. So in some sense, you can say that this symmetry is also required for the equivalence to the nambu-goto action. Okay? So we can actually use we can also turn things around. We can also use as a symmetry principle. Okay, a symmetry principle, we can ask, suppose we have an action, suppose we require an action to satisfy the ABC, to be invariant under ABC, what is the most general action? Okay, and then you can essentially uniquely determine the three. Okay, we can use actually symmetry principles to uniquely determine. Actually, it's almost uniquely determined. Okay, so I will explain this almost. So now is this clear? Is the logic clear? So we do two ways. We first start with nambu-goto, and then we go to this action. But then we observe this action have these symmetries, and then now we ask ourselves, what is the most general action with such symmetries? Okay, and that's then will lead us back to this term, to this action. Except there's one more term you can add. Okay, there's one other term you can add. So that's why this is almost. Term. So I will just immediately write it down. This is called the Euler action. So this action actually have a long history. So this is called the Euler action. So this can be written as following. And so lambda is just a constant, some arbitrary constant. And R is the rich scalar for gamma AB. Okay, gamma AB is a metric. It's a two-dimensional metric. You can construct the corresponding rich scalar. So you can clearly check this action. So let me call this equation 4. So you can check easily that A4 is invariant under A plus B under A because this does not depend on X. Okay, of course this is invariant under A. And this is invariant under B because this is a covariant action. So this is invariant on B. To see this is invariant under C requires a little bit effort. Okay, requires a little bit effort, but if I write down a formula, then it will become clear. So under C, if you make such a transformation, say under gamma prime equal to exponential 2 omega gamma, 2w gamma, and then you find that minus gamma prime and r prime means the rich scalar for the gamma prime is equal to square root minus gamma r minus 2. Yeah, this is a formula which you can check yourself. I will just directly write down. And then you get one more term, but this term is a total derivative. Okay, so this term is a total derivative. And if you impose the right boundary conditions, or if you consider a compact worldsheet, then this term will automatically vanishes, and then this is invariant. Okay, so we have shown this is invariant on the on everything A to C. So essentially that's it. So these two terms are the only 3 and 4 are the only terms are invariant on the A to C. Okay, there's no other terms. So total action. Then this is our total action. So actually, some of you who knows two-dimensional gravity, yeah, maybe let me put the minus sign here. Yeah, good. So some of you who know the two-dimensional gravity will immediately point out you actually don't need to add this term, because this is actually a total derivative. So this is a property of, I only make a claim here. So this thing is a total derivative. So you can check yourself. Go back, go to your favorite GR book. Go to your favorite GR book and work out the scalar, rich scalar in 2D. And then you find actually the square root gamma times r is actually total derivative. So it will not affect your equation motion, etc. But it is important, otherwise I will not have talked about it. Because when you go to the Euclidean signature, that's the standard way we evaluate the path integral. So when you go to Euclidean signature, this is only saying that this is a total derivative is only a local description. It's actually a local description. In fact, this is actually a topological term. So locally, you can write it as a total derivative. But if you put on the topologically non-trivial manifolds, then you cannot do it globally. And so in fact, in the Euclidean signature, it's actually, I don't know whether this is due to Euler. This Euler action is actually equal to lambda times chi. And the chi is equal to pi, which is defined to be. So now it's R is actually 2 minus 2h. Okay? And the h is the genus over surface. No, this is only in 2D.
This is only true in 2D.
Yeah, in 2D. So in 2D, even though this is locally a total derivative, but it's not a global total derivative, but you cannot write it as a total derivative globally. And so when you integrate it over a non-trivial manifold, a manifold with a non-trivial topology, actually this is non-vanishing. It's non-vanishing. Actually give you this Euler number. So for example, if you integrate it on the sphere, then you find that this number is 2, corresponding to h equal to 0. And if you evaluate on the torus, then you find that this is 0, etc. Okay? So 1 second. So from the Euclidean perspective, so in the Euclidean path integral, so Euclidean path integral, this S minus, so this exponential S Euler term just give you exponential S lambda chi. Okay? So now you may ring a bell, because this is precisely the Fudge term I added before when I say when we sum over different genus, you have the freedom to add a chemical potential, lambda times the Euler number. And actually, this is dictated by the symmetry. And if you include the most general terms consistent with those symmetries, then you are required to include this Euler term, and then you have automatically weight. Then you would be automatically have a weight for different genus. Okay. But for this theory, the lambda is actually but lambda is arbitrary constant. So the choice of lambda is still arbitrary. But but this does give you a non-trivial weight. So this is weight different genus. Yeah. Any questions about this? Yes?
So wouldn't if you have a non-trivial topology, wouldn't the boundary term from the symmetry also be non-trivial? So wouldn't the symmetry break?
Sorry?
If you have a non-trivial topology, wouldn't the total derivative boundary term, total derivative in the symmetry transformation also?
No, they're different kind of. They're different kind of. No, there's no global issue here. This is just an ordinary function. You have to write down this explicitly to know it. Yeah. Yes.
So the claim is that this should work no matter what value of lambda that we put.
Yeah.
So this is why you were able to put in that factor in the sum, because we could make lambda equal 0, in which case we don't have it.
Yeah. Lambda is lambda is not dictated by symmetry.
Right.
So lambda is just a free parameter here. Right. But in principle, such a term exists. Yeah. Yeah. Just lambda equal to 0 is a special case. Yeah. Yes. Yeah, in the Minkowski case, it's a little bit tricky to talk about topology, etc. And so that's why we always, when we do the path integral, we always go to Euclidean signature. Yeah. And for example, later when we quantize the action, which we work with a Lorentz signature, and we only care, say when we solve equation motion, we only care about the local structure, then we can just ignore this term because this does not contribute to the local structure. Good. So to summarize, from the two-dimensional, so again we can think of this as a two-dimensional field theory coupled to in the curved space-time. From that two-dimensional perspective, this is a global symmetry. Okay, so A is a global symmetry because this does not depend on, because the symmetry does not depend on the sigma and the gamma and sigma and tau. So this should lead to conserved charge, conserved current, conserved charge and conserved current. Okay, so we will see later this indeed play a very important role in physics. And the B and the C are what we call the gauge symmetries or local symmetries because they depend on sigma and tau. Okay, they have arbitrary dependence on sigma and tau. There and here can also depend on sigma and tau. So this is what we call the gauge symmetries. So for those of you who have studied quantum field theory 2, or even quantum field theory 1, for those of you who have quantized QED, you know that the gauge symmetries are not genuine symmetries. They just tells you they are redundant degrees of freedom. Okay? And they're just redundant degrees of freedom. And then when you quantize a theory, then you need to get rid of those redundant degrees of freedom first. And because otherwise you will have a consistency problem. And the process of getting rid of redundancy problem, to get rid of redundancies are called gauge fixing. Okay, so that's what we will do a little bit later. So in principle, you can just proceed to do the path integral quantization as we did before. And the path integral quantization is conceptually simple and geometrically elegant, but it does not give you, say, string theory spectrum, and because it's a path integral, etc. If you really want to find what are the spectrum of the string theory, you actually have to do a standard canonical quantization. So that's what we are going to do next. Okay. So now we are going to quantize the string in the canonical way. There are many ways of doing it. I will use the simplest way, say technically simplest way, also conceptual simplest way. It's called the netcom quantization. And the meaning of this word will be clear. So the basic picture will emerge from this quantization is that each oscillation mode, so if you have a string, then it can oscillate, right? Because that's what string does. It can oscillate. So each oscillation mode, so the bottom line is that we will show that each oscillation mode of string give rise to a space-time particle. Okay, from the string point of view, it looks like some kind of oscillation of string, but from the space-time point of view, it's like a space-time particle. In particular, if you have a closed string, then that will give rise, say, graviton. Say one particular mode will give you graviton, and then and many other particles. Actually, you have an infinite number of particles from string because there's an infinite number of vibration modes of a string. And if you have an open string, say the string which does not close, and then actually then you find the gauge field arise in one of the vibration modes. Say this can either be photon or gluon, etc. Okay. Yeah, so this is the thing we like to show. Yes.
What are the gravity?
Oh, there are infinite number of particles. So because the string can oscillate in the just any string can oscillate in principle in infinite number of ways. And if each oscillation mode is corresponding to a particle, then you can have an infinite number of particles.
Can it be what's qualitatively different between graviton and photon?
Oh yeah, they're completely different from graviton and photon. They're just completely different particles.
So what kind of particles in the same class as graviton? What other particles in the same class as graviton?
Depending on what you mean by class.
What can you give a second item in the same line as graviton? What else can it be?
Oh, for example, massive spin 2 particles, massive spin 3 particles.
So anything with spin more than one.
Can also have scalar particles, massive scalar particles, but they're all massive.
Do they have to be bosons? Do they have to be bosons?
They can be fermions. In this theory, they can only be bosons, but we can play tricks to get fermions.
So does this predict that, so if you were to have a string theory model which would reproduce the standard model, does this basically says that at higher and higher energies that we expect to always see like new types of particles or something?
Yeah, that's right.
Interesting. Okay.
Yeah. But we will see. You need to go to a specific time. You have to go to a specific energy scale to see it.
So we can see how there's space.
Yeah, that's right. Yeah, but that space is determined by some energy scale, and that scale can be very high.
I see. Okay.
Okay, so now we will quantize this theory using canonical quantization. Okay, so by canonical quantization, so let me remind you, this is the procedure. So this is the procedure we typically explain, say in the second day of free quantum field theory, and so we are doing the same thing here. So the quantization procedure is the following. The first step is you write down equation motion. Okay. And in the case which you have a gauge symmetries, then we fix the gauge symmetry. And the third is find the complete set of classical solutions. Okay. And the fourth is you promote the classical field on the worldsheet fields, say the X or gamma, to quantum operators. Okay? So the quantization procedure is that you promote them to quantum operators which satisfy the so-called canonical commutation relation. And the previous equation motion then become the operator equations for those operators. Okay? In particular, then the classical solution you find in 3 become the solutions to operator equations. Operator equations. And in particular, the parameters we use to parameterize your classical solutions so those become, say, the creation and annihilation operators. Just as what we do in the free field theory quantization. And then the last step, once you have the creation and annihilation operators, then you can just find the spectrum. By acting the creation and annihilation operators on your vacuum, then you can find the spectrum. So find the spectrum. So this is the standard procedure. So this is almost exactly the same as how we quantize a free scalar field theory in quantum field theory 1. The only tricky thing is this. This is a system with gauge symmetries, that's the only tricky thing here. Okay. Any questions here? So now let me just again say some boundary conditions we are going to use.
What are the parameters in classical solutions in case of electromagnetic?
Sorry?
What are parameters in classical solutions for the case of electromagnetic field?
What are the
Parameters in classical solutions in case of electromagnetic field?
is these different modes for your classical waves. The amplitude for your different classical waves.
It's not momentum polarization.
Yeah, it is like that. Yeah. For scalar field theory, just for harmonic oscillator, you can write a cosine a exponential ikx a exponential I omega x plus a star exponential minus I omega x. So a is the parameter, and a star become creation and annihilation operator. Yeah, it's the same thing here. So we will consider both closed and open strings. So both closed and open strings. So if you have a closed string, then just by convention, we always take sigma to go from 0 to 2 pi. So the closed string means it's closed. Means closed. Then we take this from 0 to 2 pi. That means whatever function should be a periodic function of 2 pi. Okay, should be a periodic function of 2 pi because it's closed. Okay. So the same thing with gamma. Same thing with gamma. Okay. But if you have open string, by convention, we take sigma goes to 0 to pi. So one end of the string is at sigma equal to 0. The other end is at sigma equal to pi. So for open string, so here is sigma equal to 0. Here is sigma equal to pi. Okay? So the sigma is the direction along the string. So we need to, for the open string, then because you have boundaries, then we need to supply boundary conditions at the endpoints. Okay? Endpoints. Good. So now with this setup, we can now just follow that 5 steps. Okay? We can just follow that 5 steps to quantize the string. So do you want to have a break? Okay, let us start. So we just follow these steps. First, let's write down equation motion. Okay. First, you just do a variation of gamma AB. Okay. So gamma is the worldsheet metric from the point of view of two-dimensional field theory. So gamma is a worldsheet metric. When you do variation over gamma, essentially what you get is the stress tensor for this is the stress tensor for this worldsheet theory. Okay. So when you do the variation over gamma, essentially it's just the statement that the stress tensor has to be 0. Okay? And then you can work this out explicitly. So the stress tensor, which I call TAB, Okay, so you just do the variation of that action respect to gamma AB. This is what you get. You find that this thing has to be equal to 0, and I just call this thing TAB. And this TAB is essentially the stress tensor of this. If you view it as a scalar field theory, so this TAB is essentially the stress tensor of this scalar field theory. Okay.
I have a question.
Yeah.
If we add the topological term,
Yeah.
there is a rich scalar there, but there must be Einstein tensor equals to TAB.
No. Because there's a total derivative term in 2 dimensions. Total derivative never contribute to equation motion. Yeah.
So, but if we just calculate the Einstein tensor for that R in 2D, we'll get 0. Right?
You will get 0.
Okay.
Yeah.
Sorry,
Yeah.
so you just said that from the equation of motion of gamma AB, you can get gamma AB equals to 1/2 lambda HAB. Is that?
Yeah. Yeah, it's the same thing. It's the same thing. I just, yeah, if you, yeah, but this is a very good question. Let me do that here. Say, if I write gamma AB equal to 1/2 lambda HAB, I can write this lambda explicitly. Then I can multiply this by HAB on both sides, and this means HAB, gamma AB equal to lambda. Okay, okay, that means lambda is equal to gamma AB times HAB. And so this equation I can also write it as gamma AB is equal to 1/2 HAB, gamma AB, HAB, or gamma CD. Which you can show is equivalent to that equation. Okay? Or maybe I should do, let me see, I should do gamma AB. No, I should do that one. Yeah, it doesn't matter. I can do, to be exactly the same as that equation, let me just do both sides. I contract with gamma AB. Let me see. Maybe I contract both sides. Let me think. So that is HCD. So that is gamma AB times that thing is equal to. You can. Just take this equation. You get this equation, then you can show that equation is equivalent to this equation. Okay? Yeah, the equation is right now they're not written in an identical way, but they can show they're equivalent. So, treat it as your homework. So now if you look at equation motion for x mu. Look at equation motion for x mu, then this is just like a standard scalar field. So this just gives you okay, let me call this equation 6. So these are all your equation motion. If you have an open string, then when you do the variation, of x, you have to do integration by part. Then in the standard story, you have to then you will have a boundary term, okay? But you actually have to be careful about that boundary term. For the open string, you will get the boundary term. Which is given by theta mu, gamma, sigma, B, partial B, x mu. Evaluate sigma equal to 0 and pi should be equal to 0. Okay? So this just comes from when you get the second order equation, you always have to integration by part when you do the variation. That just comes from the boundary term of that variation evaluated at the end point of the string you have in the sigma direction. Okay, is it clear? Good. Again, I will not go through all the algebraic details. You should check those details yourself. Okay. You should check them, and if you find mistakes, it's greatly encouraged. Yeah, we'll add your points. If you find mistakes, then I will add your points. If you have found enough mistakes, then you may not need to do the p-set anymore. So this tells us we can actually impose two kinds of boundary conditions. Say delta x, either delta x mu have to be 0. Say evaluate the sigma at 0, sigma equal to 0 or pi equal to 0. Sigma 0 or pi does not have to be the same. Or this thing is 0, gamma sigma b. The reason the sigma here, because we are interested only in the boundary term in the sigma direction. The boundary term in the time direction we never care about. Because the boundary term in the time direction, we always assume in the far past and the far future, nothing happens. We always assume that. But you cannot assume a boundary condition at the spatial condition. You have, in the spatial boundary, you have to be careful because we have a finite spatial extension. Okay, so that's why this sigma. So a lot of possible boundary conditions, gamma sigma b times partial b x mu, say evaluated at sigma is equal to 0 or pi equal to 0. So this is normally called the Dirichlet boundary condition. This is normally called the Neumann boundary condition. The reason this is called Dirichlet boundary condition because if delta x is fixed at the end point, means that the value of x are not allowed to vary. So this is normally called the Dirichlet. Okay. And for the Neumann boundary condition, you only constrain the derivative. And the value of x can be anything. And you only constrain the derivative. So this is called the Neumann boundary condition. Okay? So for simplicity, so later we will treat both of them. But for now, let me just look at this one, because this one is slightly simpler. Or slightly simpler. So for the moment, let me just consider the Neumann boundary condition. Okay? So now the second step is fixing the gauge. Second step is fixing the gauge. So we have two gauge freedom. One is to change the coordinates, and one is to do a scaling. Okay? So before we fix the gauge, let's do a little bit of counting. So here I can change coordinate by arbitrary two functions. Okay? So here I essentially have two arbitrary functions degrees freedom of the gauge freedom. And here I have one arbitrary functions of gauge freedom because I can choose omega arbitrarily, W arbitrarily. And if you look at gamma AB, the worksheet metric, so AB is from 0 to 1. So this also has three freedom, 3 degrees freedom. Okay? So that means actually, intuitively, at least you can see, intuitively you can expect by taking account those degrees freedom, taking account these three gauge degrees freedom, you can set this gamma AB to some fixed metric. Okay, because there's only three freedom here, and we have 3 gauge freedom, and you can completely fix them. Okay? So so now let me erase it now. So now let me do the second step. Gauge fixing. Using this diffeomorphism of B, so these have 2 parameters. You can show that you can take just make a coordinate transformation, take any gamma AB. You can show that by using a coordinate transformation, you can transform the gamma AB to the following form. Okay? So I will not prove it here, but I urge you to go back to try to convince yourself this fact. Okay? Just by using the coordinate transformation, start with generic gamma AB, you can make a coordinate transformation so that in the new coordinate, the gamma AB is only given by a prefactor times the Minkowski metric. And now we can use the C, that guy, because we have the freedom to change the gamma AB by arbitrary function, and then we can just choose that function to be opposite to this guy, then we can set gamma AB just equal to eta AB. Okay? So we can use these 2 freedom to set the gamma AB equal to eta AB. Yes?
So you're saying that we make this gauge choice locally on the world sheet.
Yeah, right.
That gauge transform the metric globally to be flat metric.
That's right. Yeah, we can transform it locally into flat metric, and then indeed there is a global issue which I will not worry about it now. Yeah, because the question which I'm interested in, say the spectrum, only concerns the local questions. Yeah. For example, if you do the path integral, then you do have to worry about the global issues. Yeah.
Okay, why is that? Why don't you have to worry about global issues when you do path integral?
Yeah, because you need to integrate over all possible configurations, and you don't want to do the overcounting or countless.
Okay.
Yeah.
So we don't have to worry. So why does that mean we don't have to?
Yeah. For example, so let me give you an example. For example, if you do the genus G surfaces,
Okay.
and then say let's do Euclidean again. It's easier. Do Euclidean, then indeed you can locally transform to eta AB, then up to a set of discrete parameters, and then you have to be careful about those discrete parameters, etc. Yeah, just those global issues, those discrete parameters have to do with global issues, etc.
I see what you're saying. Okay.
Yes.
So when you are in a closed stream, how can you make it Minkowski everywhere? You have a closed.
Yeah, just imagine you have some 2-dimensional surface. Right now, let's not consider about the topology. Right now, just consider. So in this case, for the closed string, just like the simplest thing is just you consider cylinder. So this is sigma direction. This is the tau direction. Yeah, for the closed string, it's like this. For the open string, roughly just like this. And right now, we don't consider complicated topology. We just consider local question. Then we can consider the simplest topology. Yeah.
Yes. Sorry, I didn't quite get the path integral being.
Yeah, don't worry about it.
Don't you have to integrate around like both sides of every pole that you have in the?
Yeah, you have to integrate over everything, and you have to be careful about everything.
So global affects the path integral.
Yeah.
It does matter. Okay.
Of
I
course.
thought you were saying the other way.
No. The global, I'm saying the global effects are very important when you do the path integral, and if you want to do the path integral correctly. But here we're interested in the spectrum, and this is a local question. Okay. So now with this gauge fixing, we can see how the equation of motion simplifies. First, we have fixed all gauge freedom Okay. So let's look at the 6 first. So 6 just become a free scalar equation because when gamma AB become a Minkowski metric, this is just like a scalar field. Okay? This is like a scalar field. So this you can write it explicitly. So this is a free scalar field. So let me call this somehow. Oh yeah, let me call this 7. This one 7. This one 8, just to be consistent with my notes. Then I call this 9. But we still have to worry about the 5. Okay? So the 5 can now also be written explicitly. So first thing you can check is that T00 is equal to T11. So the diagonal element are the same. It's given by 1/2 partial tau x mu plus partial sigma x mu equal to 0. And the T01 component will give you partial tau x mu and the partial sigma x mu equal to 0. Okay? So I'm just writing everything explicitly. So these are the 3 components of that equation. When I set gamma AB equal to eta AB. You can easily check yourself, just plug that in. Okay? So the reason that T00 is equal to T11 is because you actually have a scaling symmetry. So in the case when this action, this is a free scalar field, a free massive scalar field, there's a scaling symmetry. And you know that when you have a scaling symmetry under the stress tensor, the trace of the stress tensor always vanishes. So that's why T00 and T11. Okay? So for the open string, we also have to worry about the boundary conditions. And so this just becomes Minkowski metric. And the sigma, only sigma is non-zero. So you just get the partial sigma x mu equal to 0. Okay, so this should be evaluated sigma equal to 0 and pi. So right now we only consider Newman boundary condition. So let me call it 12. So this is for Newman. Good? Any questions on this? Yeah.
For this Dirichlet boundary condition, I mean it's a variation. So usually we say the variation is arbitrary. Why? I mean just the delta x can be arbitrary. So it seems like only Newman boundary condition is valid.
Yeah, this is your choice. This is your choice. So what normally in the field theory what we do. Indeed, normally in the field theory, this is your choice. In the normal field theory, when you consider, say, an infinite space, we just assume everything goes to 0 at infinity, then we don't even need to worry about the boundary condition. Then the boundary term automatically vanishes. And so that's why normally in the field theory, in the infinite space, we never worry about the boundary conditions, because we made that assumption. So here, because the string have a finite length, it's a finite boundary, and then you actually have a freedom to introduce both. Yeah, you do have the freedom to introduce both. Good? So let me emphasize again. So now in this gauge, we just have a free scalar field. So this is a standard wave equation in 1+1 dimension. But this is not a free, but we're not quantizing a free scalar field theory because we still have to solve those things. We have to solve these two equations. And these are constraints. Because in this equation, in principle, you completely solve the equation. We know that this is a wave equation. You already solve x completely. But these two equations coming from the gamma equation of motion, then impose a non-trivial constraint we have to satisfy. And those constraints are actually nasty because they are nonlinear. This is a linear equation, but these are nonlinear constraints. Okay? And this is the 10, 11 are normally called the Virasoro constraints. Virasoro was a person, so this is a Virasoro constraint. Okay? And so these are nonlinear constraint equations are typically nasty solved. Okay? So now let's first solve the easy equation. So let's go to the third step, trying to solve the equation of motion. So now we have fixed the gauge, and now we try to solve the equation of motion. Okay? So for people at your level, I can write down the equation of line, a solution of line immediately. So I can have a constant, of course, satisfy this equation. I can have a linear term in tau, which of course will satisfy this equation. For a closed string, in principle, I can also have a linear term in sigma, but that won't satisfy the periodic boundary condition. Periodic boundary condition, so that's not allowed. And then I can add the traveling wave solutions. So this is a left moving wave, or right moving wave, and this is a left moving wave. Okay? So this is a full set of solutions to so x mu are arbitrary constant. X and mu and v mu are arbitrary constant. And the xl and xr are arbitrary for closed strings. For closed strings, say xl and xr just are independent. Should be independent periodic functions. Of period 2 pi. Okay? Because they have to be, so xl and xr are a function of single variable. And they have to be periodic in sigma, means have to be periodic. This as a function. So these are the periodic function. Okay, is this clear to you? Do I need to explain this equation? Good? Yes?
Why a function of tau minus and plus minus the sigma?
It's because you have a traveling wave, because it's a yeah, you can, first you can immediately see this satisfies this equation. And then you can easily convince yourself these are the only solutions. In the sense that the because these are the two arbitrary functions, there's no other choice anymore. Yeah. Any more questions on this?
Are you going to include the sigma linear term in open string for open string?
Also not for other reasons. Yeah. Not for the Newman boundary condition. Not for this boundary condition. Yeah. Now we'll come to open string. So for open string, you can then we have these. You can check that if you have a linear sigma term, will be incompatible with this boundary condition. So we don't worry about that. And then from this equation, then plug that into this equation, we conclude that the XL prime tau should be equal to XR prime tau at sigma equal to 0. Okay, and XL prime tau minus pi should be equal to XR prime tau minus pi, tau plus pi at sigma equal to pi. Okay, so you just plug this into here. So the first two terms does not matter, and then you just have the last two terms. So the last two terms, then if you evaluate it at sigma equal to 0, then you just get the this equal to that. And if you evaluate the sigma equal to pi, then you evaluate then find this. Okay?
Professor, I have a question.
Yeah.
Why is it that you don't package those original two terms into the right and left functions? So why is it that you write x mu plus v mu tau? I mean,
because those equations, because those don't have this form. They're not in the form of tau plus sigma or tau minus sigma. No, this is just tau. This is not tau plus sigma. Now I can package in that form. It doesn't matter. I'm just saying here I'm not doing it.
fine.
Yeah.
Okay.
Yeah. What I'm saying, these are trivially periodic functions, and yeah, I just separate that.
Fine. Okay.
Yeah.
I see.
Okay. So now you from here you can find that. So this equation tells you that XL essentially equal to XR. Okay. So up to a constant we can absorb into x mu, for example. Then these two functions should be the same. And if we take these two functions to be the same, then this function tells us this is a function is periodic. The second line tells us this is periodic in 2 pi. Okay? Yeah, actually, I think I'm with a minus sign here. So if I take the sigma derivative, I can put a minus sign here. But these two conclusions still are right. Yeah. Okay. So now, for both open and closed string, we have solved the line completely. Okay, we have solved line completely. Any questions about this? Okay. But we still have to solve 10 and 11. Okay. So what 10 and 11 does is to impose some non-trivial constraint between XL and the XR and the X mu and V, etc. Yeah, you just say plugged in this most general solution into 10 and 11, it will impose some constraint on those functions. So I urge you to try it a little bit yourself, and those equations are not nice equations. They're not nice people. Yeah, they're not nice equations. And so at this stage, we face a decision. So when you see these 10 and 11 are hard to solve, then you have a decision to make. Yeah, whenever you have something you don't know how to do immediately, you have a decision to make. You have some decision to make. Or you just give up. And first, so one option is that we can just quantize this theory. We know how to quantize this free scalar field theory. we just quantize this free scalar field theory first, and then we can construct the Hilbert space, etc. And then we can impose those constraints at the quantum level. Okay, we can impose those constraints at the quantum level. Yeah, so this is one option. The second option is that you find some ingenious way to solve those equations so that you can actually find independent variables. Okay, because those are constrained equations, means some degree of freedom are not independent from some others. So alternative is that you just solve it and find the independent degree of freedom, and then quantize only those independent degree of freedom. Okay. So the first option, this stage is easy because you can quantize a free scalar field theory. But the process of imposing the constraint at the quantum level is actually rather tricky. So I will not go there. So I will do the second method. Rather, I will try to solve this constraint, find some trick to solve this constraint, and then quantize independent degree of freedom. Okay? Is it clear? So I will take the second approach. So this is the idea of the light quark quantization. Okay? So this is the idea of going to the light quark gauge. So this is an ingenious way to solve those constraints. Okay? And it was first developed by 4 people, including our colleague here, Jeffrey Goldstone, who was among the first people to quantize this theory using the light quark gauge. Actually, they quantized the nambu-goto action. They did not quantize this theory. They quantized the nambu-goto action using the light quark gauge. Yeah. So the key idea is the following. Is that after fixing this gauge, after fixing gamma AB equal to eta AB, there actually still some residue gauge freedom. You actually have not fixed everything. Okay? By residue gauge degree of freedom, say if you fix the gauge completely, then that means that any operation which previously what we did B and C, when you act on gamma, will take this away from this configuration. Okay? So by residue degree of freedom means I can still find the combination of coordinate transformation and the Weyl scaling, so that after those operations, I'm still going back to this metric. Okay, is this clear what we mean by the residue gauge freedom? Good. So to see this, I have to introduce so-called light cone coordinate on the worksheet. I introduce sigma plus minus equal to square root 2 tau plus minus sigma. And then the worksheet matrix can be written as minus d tau square plus d sigma square, because we take the Minkowski matrix. So this can be written as minus 2 d sigma plus d sigma minus. So now here is the key observation, is that this matrix is preserved by the following coordinate transformation. I take sigma plus goes to sigma tilde plus, which is only a function of sigma plus. Okay? And sigma minus goes to some function sigma tilde minus, some new coordinate sigma tilde minus, which is only a function of sigma minus. So if you plug this in here, then you find under this transformation, under this coordinate transformation, we get this ds tilde square. This is just, you just plug this in here. This is, say, 2d sigma tilde plus 2 sigma tilde minus, you go to new coordinates. And in terms of new coordinate expressed in terms of original coordinates, you get 2f prime sigma plus g prime sigma minus, and the d sigma d minus. Okay? So now the key is that under this coordinate transformation, you only transform your metric by an overall prefactor. And then you can get rid of by Weyl scaling. It's preserved by this, followed by Weyl scaling. Because this coordinate transformation only change your metric by an overall prefactor. And any overall prefactor you can get rid of by Weyl scaling. Okay, is this clear? So we actually still have some residue gauge freedom left. Okay? So now we can use this freedom to do something good for us. To do something good for us. So, so this new coordinates, say in this new coordinate, tilde coordinate, tau tilde, then have the form, say, of square root sigma plus tilde plus sigma tilde minus. Okay? So these have the form 1 over 2 f sigma plus tau, and the g is sigma minus tau, say tau minus sigma. So I have this form. So in this new coordinates, so when so you can change the coordinate. So you are allowed to make this kind of coordinate change. So you are allowed to make this kind of coordinate change. So the residue. So the residue degree freedom means we are allowed to make this kind of coordinate change. Okay. And that means, and you see, this is precisely the combination of this form. A left moving wave plus a right moving wave. Okay? Okay? So that means we can use this freedom. We can choose. So this means we can choose f and g so that tau is given by any combinations of this x, the solutions of x, okay? Because solutions of x precisely have this form. So what we will do is we will, maybe should I erase this? Yeah, let me erase this because I think you are all, or you all know this. So at the level of equation motion, you have the freedom essentially choose that tau tilde to be any combinations of those x. Okay, because those x precisely have that freedom. And the smart choice is what we call the Lightcon gauge, is you choose, we can choose so that tau tilde is proportional to, so called x plus. And the x plus is defined by square root 2, say the zero component of x plus, say, some one of the spatial directions. Okay, say I take 1. So to fix this gauge, to fix this residue gauge freedom, I have the freedom to choose tau tilde to be some combination of x. And this is the combination I will choose. So this is what we call the Lightcon gauge. So I will suppress this tilde. So in the Lightcon gauge means we go to a coordinate so that tau become equal to x plus and up to some constant which I call v plus. Okay? So v plus is some constant. Is this clear to you? And this is so-called Lightcon coordinate in the target space. Okay? So this corresponding to identify the worldsheet time with the Lightcon time in the target space. Or in other words, x plus equal to v plus tau. So this is what we call Lightcon gauge. So why do we want to do that? And the ingenious thing is the following. Is that if you write x mu, so we can write x mu as x plus, x minus, and xi, and I come from 2 to d minus 1. So x plus and x minus is x0 and x1. So and then so let's write in this form. Okay. Then you can easily check yourself, or you maybe already know it. Is that this particular contraction is given by 2 x plus x minus plus xi squared. Okay? In particular, you notice, just as here, which you have this off-diagonal structure, this kind of contraction have this off-diagonal structure in x plus and x minus. And this turned out to be key. Okay? Yes?
Do you mean for that to be 0 and 1 and then that to be plus minus?
Sorry?
Do you mean for that to be 0 and 1?
So these two are equivalent to x0 and x1. Then we include the rest, starting from I equal to 2 to d minus 1. So x mu, so x mu have x0, x1, then what I would call xi, which I start from 2 to d minus 1. I just rename these two to be x plus and x minus. Just change this x2 to x plus and x minus.
Oh, I see. Okay, fair enough.
Yes? Yes?
So when we do another one, I saw the Weyl scaling is already fixed when you trying to fix gamma AB into eta.
No. No, I'm just saying, no, I do these two operations by, in sequence. So I do that operation, and then I choose the Weyl scaling so that I precisely cancel this. Of course, if you just do a single Weyl scaling, this will be violated. But if I do that two operations together, then this will be preserved. Yeah, I have to do that two together. Yeah, if you do a single one, this will be violated. Okay, so this is the key point. So we will see that this structure will play a key role. So this is the smart thing which our friend Jeffrey did. This is, in fact, the ingenious thing our friend Jeffrey and his friends did. So now let's look at this. Now let's look at these two equations. Okay. Now let's look at these two equations. So the first thing. So now let's can look at 10 plus 11. Give us. So first, let's note, because of this, partial tau x plus is equal to v plus, and the partial sigma x plus is equal to 0. Okay? because there's no sigma dependence there, only a tau dependence, which is linear. And then we just plug it in. So let's look at it here. Yeah, let's forget about the 1/2. You can also think about the 1/2. Doesn't matter. So look at plus and minus structure here. Use this here. Then you get minus 2 v plus partial tau x minus, okay? Then plus partial tau xi square. This is for the first term. And the second term, the x plus and the x minus part is 0 because of this, and because of the off-diagonal structure here. Okay? Do you see it? So the first term here would be partial tau minus 2 partial sigma x plus partial sigma x minus plus partial sigma xi square. So this would be 0. But our friend here is 0. Because of that, it's 0. So now we can erase it. So now let's change this to the other side. Okay? Let's change this to the other side and then change this sign. So the equation I get is the following. Okay, so this is equation 10. So now let's look at equation 11. Okay, 11 is, so we have partial tau x plus, then partial sigma x minus, then equal to partial tau xi and partial sigma xi. And this one just gives us v plus. So that two equation become this two equation. So let me call this 14. This is 15. So is it clear to you, these equations? So if it's not immediately clear to you, just check it yourself. Okay? Urge you to do the check, because then you will see the magic. Then you will see the magic, and the beauty of this trick.
In case of equation 11, wouldn't it be d tau x minus d sigma x plus?
Sorry?
D tau x minus d sigma x plus. So
Yeah, that's 0. Because partial 0 x plus is 0. So that's why there's only 1 here, not 2, because the other term is 0. Okay? So now the beauty of these two equations is that it express the x minus solely in terms of xi. So this 14 and 15 tells you is that xi, x minus, can be fully solved in terms of xi's. Because this equation gives you the tau derivative of x minus. This equation gives you the sigma derivative of x minus, and all expressed only in terms of xi. So the x minus is completely solved, completely expressed in terms of xi. And then we have solved those constraints, similarly elastic constraint, explicitly. Okay? So right now we are doing a little bit fast. I urge you to go through the algebra yourself to appreciate the beauty of this step. So we conclude that independent degree freedoms are only xi's. Because x plus we already know by fixing the gauge, and x minus now is completely solved in terms of xi, so the independent freedom are only xi's. And this will make our life very easy, because xi are just free scalar fields. Xi just free scalar field with the right kinetic term. You have also get rid of x0, because we said that before x0 we have a long sign kinetic term. But now we are only independent degree freedom are only xi's, and they have the right number of kinetic terms. They have the right sign for the kinetic term, and they are just free scalar fields. So we can quantize them as what you did in your first day of quantum field theory class. And then you have quantized the string theory. Then you have quantized string theory. Okay? Yeah. I think I'm going very slow here. Maybe I'm a little bit too emotional. Yeah, anyway, so maybe let's stop here. And next time maybe we'll talk about, the next time is a little, then the next time then we will just quantize those things. And those equations still will give us some very important informations. And then we will quantize those things, and then we will be able to see that the string theory contains gravity. It contains graviton. Okay.